Alright, welcome back. Did you guys miss my voice? I'm sure you did. Alright, so we're taking a look at this math task 4.4, which is pretty simple. The kind of title says it all. Is it linear, exponential, or neither? Okay, so we're just kind of looking at these and trying to decide. Is the pattern a linear pattern? Or in other words, think of that arithmetic pattern. Is it, equal differences over equal intervals? How's the slope looking? Are we adding the same number? Are we subtracting the same number? What are we doing there? Okay. Exponential, that's our geometric. Our equal factors over equal intervals. So multiplying, dividing, that's what we're looking at here with the exponential. How is that growing? Okay, that same factor. And then neither, the last one, if it's not arithmetic or geometric, well then it's got to be neither. That's kind of our last way to look at it. So the way this should be going, make sure that you're trying these beforehand. We'll probably go a couple at a time, and then so the substitute you have will pause, give you a few minutes to work on a couple of these problems. That's where you work and try to figure it out, and then you go on from that, and we'll watch a couple and move through it and just move through it that way. So that's basically where we're going. Now in the instructions it tells you to give at least 2 reasons. If you can, that's great. If all you can get is 1 reason, then I'd rather have 1 than none. So try to get 1. If you can try to think of it a different way while you're waiting, try to think of another way that you could try to show that that is where it's going. So let's get started. So make sure that we get paused, take a couple minutes, do these 2, and then let's watch them. So hopefully you've already taken a look at those 2. Alright, so question 1 and number 2. Now question 1 is giving it to us in graph form, right? And right off the bat you should notice it looks like a straight line. For most of you, that's probably enough of a reason to say, well, it's a straight line, so therefore it's linear. Because it's a straight line. Now you got to remember the linear grows by that constant. That slope is always the same. Okay, so if we could check this slope to see if it's always the same, ideally that's what we would want to do to double check that. Would be to take a look at that slope. Now these numbers aren't the easiest to deal with, right? But if we turn them into decimals, we've got negative 1.50 and 0, negative 0.5. So basically, as this goes down a half, it's going to the right 1.5. So its slope would be negative 0.5 over 1.5, because we're moving 1.5. Okay, which if we wanted to double that, that would basically be negative 1/3. So as it goes down 1, it's going to the right 3. So if we went down a half, to the right 1.5, so there's 1.5, that looks pretty close. So that slope looks pretty close to me that that's what we've got. So yes, it is linear. Okay, either because you see that it's a straight line, or because you're kind of looking at that slope and getting a pretty good idea that that next one is where it should be. It's moving at that constant rate. Okay, that constant rate is where it keeps going. So number 2, taking a look at this. This time they give it to us in a table. Now sometimes you can take and rearrange these or put it in a different model, a different way of representation of it, and sometimes that could be useful. For example, number 2, maybe I wanted to instead make a graph here. And so, I went 1 and 64 up here, and then down to 32, to 16, to 8, to 4, and then 1, 2, 3, 4, 5. Okay, if I graph this, the way I graphed it was good because I cut it in half. You get that same you're going to get a curve like that. When you see a curve like that, that should key you into the fact that it is going to be geometric or exponential. The other way would be to see, okay, how do I get from 64 to 32? Oh, we subtract 32. From 32 to 16, we're subtracting 16. 16 to 8, subtracting 8. So it's definitely not arithmetic, it's not linear. Okay, but if I divide by 2, or in other words, times by a half, then yeah, that's got that geometric pattern which would make it exponential. Okay, and it makes sense because, in a tennis tournament, you only have one winner that moves on, so half the people are eliminated after the first round and so on. Okay, so either, seeing that pattern where you're times them by 1/2 or dividing by 2 would be reason enough to show that it is exponential. You could make the graph and see that it's also exponential. Okay, so there's a couple ways that you could figure it out that way. You could even make the equation, which, you're assuming it's exponential when you make that equation, but then you could use it to check to make sure it works. Now, if we think about it, remember that we talked about continuous and discrete. Question number 1, because we're filling in it's a line, we fill in all the circles, that would be continuous. Question number 2, and I didn't spell continuous right. Question number 2 would be discrete, because you can't have half a round in a tennis tournament. Okay? So that doesn't make sense. You have one round, and at the end, in round 2, you have that chunk. So that would be discrete. Okay? Alright, so take a pause and take a look at the other ones. So you should have done 3 and 4 on your own, taken a few minutes to look at that, try to figure it out. So let's talk about it. So number 3, okay, notice that the x is being multiplied by the 4. That should remind you that we're adding 4 over and over again. How many times? X number of times. Right there would be enough to tell you that this is going to be linear. Okay, you could have also made a table out of that or graphed it. Would have started at 0 for your x-intercept, and then you would go up 4 every time you go to the right one. And so you could have seen that straight line and made it continuous because you can put different values of x in there. Okay, or you could have made a table and went, 0 is 0, 1 is 4, because 1 times 4 is 4 for x and y. And you would have seen a similar pattern where you're adding 4 each time. So any one of those using to explain how it's linear. Now number 4, this function is decreasing at a constant rate. So decreasing meaning it's going down at a constant rate. Well, let me show you 2 graphs here of decreasing functions. Here's a linear decreasing. Here's an exponential decreasing. Okay? Now what it means by a constant rate is that no matter where I pick 2 points, it's going to be the same angle, essentially, that constant rate. So if I look at the linear, that straight line is always going down at that same rate. Whereas if I look at the exponential, hopefully you can see that the steepness of that piece right there is different than the steepness of that piece right there. So that's not a constant rate. Okay, because of that constant rate, that would make it a linear. So, pause it and take a look at the next 2. Okay, so hopefully you looked at that, and number 5 probably gave you a little bit of a trick, because you may look at this and say, oh, it's curvy, just like the exponential, so you may want to call it exponential, but you've got to double check. There has to be a reason why. And what we can do is make a table out of this. So when x is 3, y was 0. When x is 4, y was 1. X is 7, y is 2. And when x is 12, y is 3. Okay? So now what does that tell us? How is this growing? Okay? Well, are we multiplying by it? Looks like on the y values we're just adding 1 each time. And on the x values we're adding 1, then 3, then 5. Okay, this pattern isn't multiplying. There's no multiplying I can do to get these to work out to be the same. So this one's a neither. Okay, we are not adding or subtracting or anything like that. Okay? Now, number 6 says a person's height as a function of a person's age from 0 to 100. So, this one you kind of got to think through it. Now, you'd want to make a graph, and it'd be mainly in that positive quadrant because you can't make it negative. People don't have negative ages. So, at 0, how tall they are, and then out to 100, right? So we're thinking, you'd have all these ages here, and you'd want to see your height. So this would be the age, this would be the height. Say this would be like 5'10", and various other heights. So then you'd kind of think through it. Think about yourself. When you were 0, you were pretty teeny. Okay? When you got to be 1, you got a little bit bigger, 2 bigger, 3 bigger, and so on. But then it seems like around, junior high, for girls a little earlier, around the end of elementary. For boys, usually around junior high, you usually grow quite a bit. And then when you're around your, teens, 20s, you're kind of leveling off on your height. And sometimes the older you get, you start to go down a little bit. So your graph would look something like this. Okay? Which, if you look at it that way, because your height stays constant for so long, okay, if we took sections of it, it may look like a linear, like this, a straight line, right? Has that constant height. Okay, but we got to take the whole graph, and it doesn't ever have a constant rate, and you're never multiplying by it. Okay, we're just not getting bigger exponentially, so once again, this is a neither. But you had to kind of think through it. So, stop and take a look at 7 and 8 now. Okay, so you should have seen, tried these ones out. Now, number 7 hopefully was a little bit easier to notice. Okay. Now, notice that this x is being multiplied, so is the y. That would think about, that repeated addition. If it was an exponent, then we would think about multiplying, but it's not. So just by that fact, you could say this is going to be linear. Or you maybe wanted to rearrange it, and you added 3x to both sides. Actually, not added 3x, let's just subtract 7. You got 4y equals negative 3x minus 7 divided by 4. So we could rearrange it. Get y equals negative 3/4 x minus 1 3/4. Okay? Which, to me, that slope-intercept form, that's basically what you've got going on. And we could graph it. It'd be a straight line. We'd start here. We'd go down 3 to the right 4. So it's moving at that constant rate. So it's linear. You could graph it. You could make a table. You could do various things like that to help you figure it out, which I'm not going to spend the time looking at right now, because we're dealing with those fractions, and I'll just lose you when we're talking with those fractions. But let's instead take a look at number 8. Now we've got a table. So let's see what's going on here. Well, 2 to 0, we're adding 2. So we're adding 2 each time. So our intervals are equal. So this could be arithmetic or geometric. Now let's see what's happening here. 23 to 5, we'd be subtracting by 18. Can we keep subtracting by 18? 5 minus 18 would be negative 13. Minus 18 would be negative 31 minus 18. Yeah. So we're subtracting that same number. So yeah, this one would also be linear. Okay, you can see from the table, equal intervals and equal differences. Okay, that's what linear and arithmetic we're talking about. Now we could graph it and we'd see a straight line. It would look something like this. We'd start up pretty high. It'd be pretty steep. And then go down, and then down, and then just keep going down really steep. But it'd be going at that constant rate, which would give it that straight line, because we're subtracting 18 every time. Alright, now number 9. Oh, hold on. You need to pause it before you do these on your own. Okay, I almost got ahead of ourselves. So once again, let's take a look at and see what we need to do here. Now the first thing I would suggest we do is that we take this table and that we rearrange these and put these in order. Okay, so I'd go 53 and 4, 58 and 7, 62 and 6, 67 and 11, 70 and 9, and 74 and 13. Okay, now let's see if there's any sort of pattern going here. Okay, this would be adding 5, adding 4, adding 5, adding 3, adding 4. Oops, wrong button. Too close there. There we go. Okay, so it doesn't look like my intervals are even the same. But then, let's see, we're adding 3, subtracting 1, adding 5, subtracting 2, adding 4. Now, to see if there's a constant rate, we'd need to compare that. That would be 3 over 5. This would be negative 1 over 4. This would be 5 over 5. Negative 2 over 3. None of these will reduce to the same thing, which pretty much means that we don't have a constant rate, and even multiplying, there's no way that that's going to get the same thing to work out. So that would be neither. Okay, now number 10, the number of cell phone users in Centerville as a function of years, if the number of users is increasing by 70% each year. So once again, think about a graph. So this would be years. So we count those. This would be number of users. Okay, so now the way you got to think about it is, what does it mean to increase by 75% each year? It basically means that we're multiplying by 0.75, and that's how many more people there are going to be. Okay, so say we started out with 10, 10 users, and then in that first year we'd get how many more users? Well, 10 times 0.75 is 7.5. So we add that to 10, and we'd get 17.5 for this year. And then the next year, we would times 17.5 by 0.75 to get a bigger number. So we're multiplying every number, we're multiplying by 0.75, so it's going to give it that curve. If you made a table, you'd go times 0.75 times 0.75, and that, so it would make it exponential. So stop, take a look at number 6 now, and go with that. Alright, so you should have taken a look at 11 and 12. 11, most of you will probably look at that and should recognize it as exponential. Okay, that's a good guess, but we should probably double check. So look at the y values. We've got 1, we've got 2, we've got 4, we've got 8. So 1 to 2 to 4 to 8. Yeah, we're definitely times them by 2. So that would work. You could have also made a table, done it that way as well. Okay, number 12. The time it takes you to get to work as a function of the speed at which you drive. Okay, so this would be kind of another one of those that you have to kind of make a function. So the time and speed. Well, for you guys it might be tough because you're not sure how to drive, but when I think about, when I drive really fast. No. Well, first of all, I have to back up, so I don't go too fast. And then I've got a pretty, sparse road that I drive on, so I'm driving faster. so I get going faster, and then I have to go to a stop sign, so that takes me back down. I have to slow down for that, and then I go through more houses, so I'm not quite as fast. Another stop sign, so when you're kind of looking at this, the speed at which you drive is going to change, right? So it's going to kind of go up and down depending on it. So, that is definitely not linear. Even though those could be straight lines, it's not a constant there. This rate of change is changing. So that would be neither. So take a look at the next ones now and go with those. Okay, we're almost done. We're getting there. So, number 13. Okay, does that look like the slope-intercept form? Or does it look like the exponential version? Okay, it doesn't. It's got an exponent, but the exponent is a 2. It's not a variable. It's a number. So that means it's not this. It does have an exponent, so it means it's not this. So it's got to be neither. If you graphed it, it would end up looking something like this. It's a parabola. So it kind of looks like it could be exponential, but it's not, because it's going back up. If you made a table, similarly it would show, like -1 would be 7, 0 would be 0, +1 would be 7, to kind of mimic that. Okay, so that's a neither. Number 14. Each point on the graph is exactly 1/3 of the previous point. Okay, so that exactly 1/3, that's kind of like times them by 1/3 or dividing by 3. Okay, think of it like this. If I started out with, let's say 90, well, what's 1/3 of 90? It would be 30. Okay, now what if I take 1/3 of 30? That would be 10. If I take 1/3 of that, where would that put me? So they're each going down, just like last time we talked about how we can tell the exponential, the rate of change, based off of that multiplying. Well, now we're taking this piece, cutting it into thirds, and that's where we get this. Then we cut that into thirds, that's where we get that. So it would be exponential. You can make a table, a graph, and just pick a starting number and go with it that way. That's kind of how you'd have to take a look at it. Alrighty, so we got the last two to talk about now. Okay, so taking a few minutes now, let's talk about these ones. So let's first take a look at number 16. So we've got f of 0 equals 1. So if we were to make a table, that would be 0, that would be 1. And then we're told to get to the next number, we take the previous one and we times it by 2/3. So we times each one by 2/3. So timesing by 2/3 would just make it go bigger and bigger. Okay, but we're multiplying by the same number each time, so that would be exponential, that geometric pattern. Okay, now number 15, another recursive, says f of 1 equals 7, f of 2 equals 7. So they gave us 2. Both 7. Now it says to get to the next term, you take the previous term and add it to the two previous terms. So that f of n minus 1 would be this, f of n minus 2 would be this, so 7 plus 7 is 14. 14 plus 7 would give us 21. 21 plus 14 would give us 35, and so, that should have been 5. Okay, and so on. So are we adding by the same number each time? No, because we added 0, we added 7, we added 14. So it isn't. Are we multiplying by the same number? No, because we'd have to times by 1, then by 2, then by, 2/3, I think it would be. So, because the growth isn't working in arithmetic or geometric form, it's not linear, nor is it exponential. So, you should take a look over those and see what we've got. Okay? Now, you need to put a bunch of work down on this. And we've got one more question I want you to write on this worksheet, and then you're going to hand it in. So, this is the question I want you guys to answer on a back of the last page, and you're going to staple them together, put your name on them, and hand them in. Okay, so what do you need to know to tell if a function is linear, exponential, or neither? So looking at all those problems we did, what is it that will tell you, if it's linear, if it's exponential, or if it's neither? Okay, that explanation you need to write down on that paper. You're going to hand that in for an assignment. So finish that up, take a couple minutes. When you are done with that, grab the homework from the substitute, and you can spend the rest of the class time working on that. And that's what we got left to do. So that homework will be due next time. The paper you're turning in now is due today. So get that done, spend the rest of the time getting everything else, that homework done you need, and we will see you next time and be ready for that performance quiz app. Alrighty.